actually in the screen?
Yep, you're right in the bullseye middle. And it's recording. I don't know where I get.
Why?
Because you're not smiling.
Well, I'm not ready to shoot yet. Hi there, everyone. Frontier Geek again. Coming back to circle around to a project that got a start a little while ago. I did a Wiring 101, which talked mostly about crimping cable and things of that nature. Now I'm going to dive a little bit deeper into actual electrical and electronic theory and see if maybe this will be helpful to some folk out there who think that tearing apart an engine over a weekend doesn't give them any pause or concern, but when it comes to trying to install a ham radio or new lighting or something of that nature, they're just terrified because it's somewhere between parlor tricks, pulling a rabbit out of a hat, and black magic. So let me see if I can maybe clarify some of that for you. So let's get right into it. So here are some of the tools that you'll probably want to have on hand as you progress further into working with things of this nature, electrical projects. A good digital multimeter is not going to be really expensive unless you're doing this for a living. You really don't need to buy a Fluke or one of those grade, which can easily be $300 to $500. This is a Craftsman digital multimeter, and I don't even remember how old this thing is. I have had it for a long time. And it has served me well. So, as I said, let me get into it. Here's the Craftsman. This one over here is a Greenlee. And let me hold that up for the camera. And the Craftsman, I turned that one on, you can see. And the Greenlee is for measuring amperes. That's current flow. And that's what this little finger grabber is for. We will get into that in a few minutes. Let me get into the basic electrical theory here first. What you need to know about volts, amperes, resistance, and conductors. So conductors you probably know. Unless you've done nothing at all with anything electrical in your vehicle, you probably know that all the wiring in your truck is made of copper. So I have some copper here. So there's one, there's two, and there's three. And I did a separate little cut video which is going to show each one of these a little more up closely. So I'm going to splice that into the video as I'm putting everything together. You'll see that. So if you didn't really get a very good view of this, don't worry about that part. I'll show that to you. But anyway, if we look at these two, pretty obvious. If I hold them up here like this, you can see that one of them is much smaller. This one looks like maybe Mama Rosa's spaghetti, and this one looks more like Groucho Marx's cigar. Now, these are all copper. So you might be scratching your head going, okay, you've got different pieces of wire here, and I know, or at least you'll probably find out when you start shopping, that this is a ton more expensive than this per foot or per roll, however you end up purchasing. And you may be scratching your head going, okay, I don't know what I'm looking for, and why am I going to spend a lot more money on the big guy? What's the point? Okay, the point we need to go first, we need to go back to high school physics a little bit and talk about what the actual nature of electricity is. And humorously, that's something that wasn't really known clearly until only a couple hundred years back. I mean, man has always known about lightning and been terrified of it because, well, yeah, lightning's kind of terrifying. It can set things on fire. It can kill you if it hits you. And if it hits a beach, it can actually turn sand into glass, which is, yeah, pretty much the definition of terrifying. So early man, even through the Middle Ages and Renaissance, really had no idea really what electricity was. People knew it was a phenomenon. They didn't know what to do with it. Then you had Tesla, Edison, Faraday, all these great scientists that came along, very smart men, who said, you know, we're not going to go with this mythological stuff. We're going to buckle down and really find out what is the physics behind all of this. How does it really work? Okay, well, how it really works, glad you asked. You go to your atom in the nucleus, or the protons and the neutrons, well, unless it's hydrogen, which only has a proton. And then on the outer shell are the electrons, spinning around like tiny little planets circling a star. The electrons, however, are really not locked in real tight. So if I apply a force, which we now call voltage, named after Volta, the scientist, I can force electrons to bust loose and travel from atom to atom to atom to atom. So I can push electricity through this wire. But I have to have some kind of force behind it. So how do we do that? Batteries, generators, or alternators. Okay? A battery only produces DC voltage. Always will, always did. Nothing will change that. It's a flat power source at one particular measured reading. 12 volts, 24, 120, whatever. Generators also create DC voltage. They do that by mechanical work, by spinning. If they're connected to your car engine or a turbine powered by waterfall, say like Niagara Falls, etc., etc. Anyway, so we're generating voltage. So along with voltage, we also have amperage. So if you think of voltage, if you want to think of a pipe, okay, think of voltage, right, is the pressure of the water rolling through it. And think of amperage as the flow. So if you got a tiny little pipe, you ain't going to get much, right? But if you've got a 6-inch water main, you've got yourself a fire hose there. There. So that analogy is pretty close, really. So voltage and amperage together have a relationship. And let me explain that to you. What is that relationship?
What's the matter with you? I'm trying to think, but nothing happens.
Okay, I know. The relationship is called pi. And I like peach pie, apple pie, yes, it's pi. Power equals voltage times amperage, or P equals IE. I being representative current, E being representative voltage. All right, so given that, we got one little other thing that jumps in that messes up the picture: resistance. In a perfect world, this wire could carry 10,000 amperes, and we'd all be happy because we could buy very thin wire, wire up all of our vehicle electronics with something extremely thin and cheap, and be really golden. If there was such thing as room temperature superconductors, we could do that. Unfortunately, so far that's been proven to be mythological. Someday, maybe, who knows? There is such thing as a superconductor at super low temperatures. I'm not even going to go into all of that. That gets crazy physics, and maybe that'll be a different video. Anyway, the more current I try to push through this little piece of wire, the more the tiny little circling planets in there are going to try to push back. They don't want to let me allow electrons to move forward. So the resistance in here and the resistance in here is going to be different. So if I wired my starter or my primary battery cables from the alternator to the battery with this guy, what do you suppose would happen? Well, if I wired the battery to this, if the engine was already running, probably very little most likely would happen, because usually once a vehicle is up and running, it's not drawing very much load. However, if I turned the key and tried to spin the starter, and I wired a starter with this little guy, what would most likely happen is this thing would glow pretty much incendiary, almost like a light bulb, and then either catch fire or just melt completely and break in half. Because this is only going to carry 5 amperes or so, maybe, before it really starts getting very upset. These two, obviously, are going to be able to carry much more. I'm going to post a chart in this video as well that shows you how to properly select wire sizes. So I don't have to go minutes and minutes and minutes running through all of this, but obviously you can tell, like I was saying, this looks more like a battery cable than this guy does. All right, so 16, 14 gauge, something along that route there. You'd be looking 20 something amperes. Wiring a lighter socket or power coupling, that you can plug a portable refrigerator, et cetera, and then when you get into generators or heavy current, obviously you're going to upsize your wire. So like I said, I'm going to post that chart. We'll talk about that. All right, so that's going to be helpful for figuring out what wire is needed excuse me, for each amount of current. And as I was saying, you can take a device, if it has a nameplate rating, and you can figure out what you're going to be needing here. Back to, again, peach pie. Power, amperage, voltage. So, got this little guy we just happened to be talking about, right? We were saying about, so we were talking about accessories here, right? So this is a lighter socket, which I'm sure everybody has seen. And it just has a long cable here and a power plug at the end. So if you notice here that some of these if you open this up, wow, what do you got? Looks like some kind of a little drug, doesn't it? Well, I'm sure that most people have probably seen one of these. This is a glass body fuse. So what is the reason to have a fuse? Glad you asked. Let me put this back together. A fuse is like a safety bridge or a gate, I guess you could say. Like I was saying, if you ran too much current through this thing, it's going to get very, very hot, and eventually the insulation is going to start to smolder, and then it will catch fire. Definitely not something that you want happening in your vehicle, especially if you happen to be driving it at the time. Really bad day. Fuse, like I said, is kind of a protectionary gate. So if I had a wire that was this thick, my fuse might look like this. The fuse is always going to be thinner than the conductor that it is protecting, so that instead of this wire catching fire, the fuse is going to let go. When the fuse burns, it does so in a safe, controlled manner inside of that little encapsulation. Some of them are plastic. That will prevent your wiring and your truck from catching fire. Very important. Always fuse as close to the power source as possible, which is normally going to be coming off of your battery. So you're going to want to go as close to the battery positive cable as possible. And I'll throw up a couple of pictures of the things that I've installed to give you an idea on that. Right, so back to voltage and amperage as we were talking about. Okay, so if I were to measure DC amperage and I wanted to know what my current flow is looking like, I would be taking this on the positive side, saying this is my voltage supply, right? This plugged into my lighter. This goes here, and then this would go over and connect to the load side, which then is going to transfer from here through to my ground. This is then going to digitally read out, when I set this to amperes, which I do, I have amperes DC and AC, and that would tell me how much current is flowing through there. Now, AC power is a little bit different. AC, P does not exactly equal IE. There's a correction factor that has to go with that because AC power is a wave. So the trough part of the wave where it's missing is power that never got delivered. So your 120 volt AC outlets in your house are only delivering 0.707 times your wattage equivalent in DC power. That's where this guy comes in. This is an amp clamp. When the cable passes through here, it actually detects the magnetic field which is created by any wire which is carrying amperage, and this can then, by nature of the electronics built in, take and figure out and display on the front exactly how much current is passing through here based on what it's seeing on this. This, however, unfortunately does not work on DC. It only works on AC. So like I showed a minute ago, to get your AC amperes, you have to measure it in a line. I might do a video, possibly just completely separately, all standalone, on just dealing with these testing equipment pieces. If anybody rings in and says, hey, yes, I have interest in seeing that, we'll see how it goes. I think that could be a good subject on its own. So as I was saying, the difference between AC and DC voltage. So the alternator in your truck is actually generating AC. So that does have that sinusoidal waveform, which looks like the Loch Ness Monster. If you look at it on an oscilloscope, it has a very humpy up and down looking waveform, which is translating between positive whatever voltage and negative whatever voltage. And the middle is obviously going to be at 0 volts, which is your baseline. So this thing is actually taking into account both of those and noting the positive and the negative and giving you that reading. So I think that's probably all we have for today. Just following, as soon as I'm done with this part of the commentary, on your screen is going to pop up on your screen that wiring selection chart, which is good for actually AC and DC really. But since we're dealing mostly with vehicles here, I would expect it's going to be DC for the most part. But that should be a big help for you to figure out if you're replacing a battery cable. Although really that's pretty easy usually. You're probably just going to mimic what was already there as far as size. Do not ever go smaller on heavy current items like that because they're going to run hotter. And the nasty thing about resistance, as we were talking about, the pushback of the electrons, is as the wire begins to heat because of resistance, the resistance increases, the hotter it gets. So you see we got a negative feedback loop here, which is going to get even worse. So the temperature is going to rise exponentially, and eventually, sometimes not long at all, you got yourself a fire real bad. So anyway, be safe out there, everybody, and I hope that this is helpful and somewhat explanatory in figuring out when adding accessories what you should be doing. Okay, a couple last observations. When buying stuff from Amazon or eBay, they often grossly, and I mean seriously, amazingly grossly, overstate and mislead on power output, very often for LED light bars. You'll see them rated at like 8,000 watts or something incredibly crazy, which obviously at 8,000 watts would require wiring that looked like this, and when you get them out of the package, the wire looks a lot more like somewhere between one of these. So that's really where you might want to actually get out your meter, like I was saying, and put that in line and actually measure the real current draw, which is what I did with the light bars that I have on my truck, and then size the wiring accordingly. And then last, you're going to make sure that you choose your fuses correctly. Fuses should always be a lower rating than the maximum current load permitted that you find in the chart, which I'm publishing. Fuse is always smaller. You don't want your wiring catching fire. Your fuse needs to, before anything else goes bad. Extremely important. Never break that rule. Never. Bad things will happen next. A lot of equipment that you may be purchasing, sometimes they will give you an actual true reading, and that will be very helpful. Another thing that you could go by is if you're installing, say, an amplifier for your audio system. Most amplifiers have a fuse already plugged into the chassis someplace, and you can go and size your wiring according to that fuse. That'll give you a very good idea of what the original manufacturer was expecting the maximum current draw to look like. So size according to that, and you should be pretty safe. And you definitely need to install a fuse that is at least as big as the one which is installed in the amplifier, or whatever the device is, if it has its own fuse, just using that as an example, up by its power source, which is usually, like I said, over at the battery. And I'm, as I mentioned, going to post some photos of what my battery configuration looks like. So I think that's pretty much it for today. I think there's probably going to be a 103. Hopefully this is providing some useful information to you and a little bit of history, and I hope you're enjoying the videos. Thank you to all who have subscribed. As of today, we're at 983, which puts us 17 short of the YouTube threshold. So I'm really fingers crossed. Fingers crossed. Thank you so much for all of you that have subscribed and stayed loyal and kept coming back for more videos. And I'm hoping to get some better video equipment and some new cameras and some lighting in the near future to continue building the quality of the channel and hopefully providing useful content. So until next time, Frontier Geek signing out. Take her out and get her muddy. See ya.